exponentials, as well as how to solve same base exponentials. All right, remember, same base isn't too bad because all you're doing is changing the bases of both sides of the function so that the big numbers match, and then you just raise it to whatever exponent you need, get rid of the bases, bring down the exponents. It's pretty much a simple linear equation or quadratic equation you have to solve. All right, so those aren't too bad. And then we also learned how to convert to logarithmic form, a little bit of how logarithmic works. Who remembers from yesterday how logs connect to exponentials? What's their connection? So why are logs and exponentials connected? They are what to each other? Inverses. So they're the opposites of each other. They undo each other. So if we had a logarithmic graph and we took its inverse, it would look like an exponential. All right. The x's and y's would flip. Now, today we're going to look more at logarithmic graphs as well as how to graph them a bit more and some other properties of logs. All right, so again, we're on page 19. That's where we're starting today. So we're back at 2.1 because 2.1 we broke up into two different sections. So the exponential section, which was more review for you guys, and then the logarithmic, which was new. So we didn't want to give you guys 2.1 all at the same time because logarithms is kind of a later on thing in the unit than exponentials was. All right. So the vast majority of logarithms that are used in the real world have bases greater than 1. All right. In this lesson, we will further explore graphs of logarithms, including their construction, transformations, domains, and ranges. So essentially, what we were talking about at the beginning of this unit with exponential graphs, but now we're looking at logarithms. And I will say this. Keep in mind that since a log is an inverse of an exponential, their key features also are inverses of each other. Hint, hint, wink, wink. And you'll see that in a second. All right. Luna, can you hit the light, please? All right. So first things first, we're going to construct a table of values for y equals 3x. All right. So this is basically coming straight from your power chart. All right. So look at your power chart. And so your x's are pretty much your exponents. And your y's is what happens when you raise 3 to that exponent. All right. So let's fill this in real quick. So 3 raised to the negative 2 power is what? 1 over 9. 3 to the negative 1. 1 over 3. 3 to the 0. 3 to the first. 3 to the second. Good. Now, the inverse of y equals 3x raised to the x power is y equals log base 3 of x. So this is the inverse. Now, we don't have to do any fancy calculations because what can we do if they're inverses of each other to get a new table for the log graph? Just switch the x's and y points. So basically my y's here would become my x's here. So that means this would be 1/9, 1/3, 1, 3, 9. And then my x's of the original table now become my y's. So it would be -2, -1, 0, 1, 2. And then we're going to take a moment and graph these. So take a moment, graph both of these sets of points, draw the two graphs. So maybe do it in a different color or make sure you label it. If you need different colors, I got colored pencils on the shelf. But just take a minute and graph these points. And the fractions, just graph as best you can. They don't have to be perfect. So if you graph them, your two graphs should look like this. So my green graph is y equals 3 to the x power. My pink graph is y equals log base 3 of x. All right. Now, once we finish the graphs, let's talk about the domains and ranges. All right. So, recall when we talked about exponential graphs on the first day that we talked about this start of this unit. So maybe look back at the 2.1 foldable that we did in your journal. What was something that typically happened with exponential graphs? You always had a what? So with exponential graphs, we always had a what? Well, all graphs technically have y-intercepts. But I'm thinking more of, why is the green line tapering off right here? Why does it not look like it crosses the x-axis? So again, look back at your notes, guys. Look in your journal because we did talk about it. Why is it that it looks like this graph will not cross the x-axis? So, do you guys remember when we talked about straight lines that they can't cross, that graphs can't cross? Does anyone remember what word I used to describe those straight lines? Starts with an A. Asymptote. So, the reason that this graph tapers off is because it has a horizontal asymptote at y equals 0. So, my graph here has a horizontal asymptote, so an HA at y equals 0. That's why that graph will never cross the x-axis. Remember, it will get super duper close to it, but it'll never cross. It'll never go into negative y values. Now, let's look at the domain here. All right. So for this, since the graph's kind of hard to look at when you draw it, we're going to look at the Desmos version of it. So in Desmos, I'm going to graph y equals 3 raised to the x power. And then since we're looking at our domain, I'm going to go to my wrench key and cut off the y-axis so I'm not distracted by it. All right. This is a good strategy, especially if you're taking the EOC. If you struggle with domain and range, Desmos, you can actually turn the axes on and off. So all that's on there is the x-axis. What do you think my lowest x value is? And keep in mind, the graph goes on forever and ever. So what's my lowest x value here? Negative infinity. What do you think my highest x value is? Positive infinity. So my domain is from negative infinity to positive infinity. What's another way I could state that? All real numbers. So you could have also drawn the R with a line through it to represent all real numbers. All right, now your range. So I'm going to hit, oops. I'm going to hit the wrench. Stop. All right, I'm going to hit the wrench key. I'm going to turn the y-axis back on, but turn the x-axis off. So from looking at this graph, where do you think my lowest y value is? 0. Now here's the question. Do you think it's going to touch 0 or be defined at 0? Or do you think it's going to get really, really close but never touch it? It'll get really close but not touch because, again, we have that horizontal asymptote at y equals 0. All right. So we're going to use a parenthesis for this 0. So the first part is 0. Now, what about the highest y value? What do you think the highest is? Infinity. It'll keep going up and up forever. So this goes to infinity. All right. So that's an exponential. Typically, your domain is from negative infinity to positive infinity, and your range is from wherever your asymptote is to infinity. That's typically how it goes. Let's look at logs now. So I'm going to turn my axes back on. So I'm going to take this graph away, or I'll keep it there for a second. So to graph a logarithm in Desmos, you would have y equals, you will hit the function key right here, and then you'll scroll down to where it says calculus. Yep. So when it says calculus right here, there's three different logs. There's natural log, common log, and then a log where you assign the base. If there's a given base, you want to use this one here. All right, so I'm going to click that, and then I can insert the 3 for the base, and then x, nope, and then the x value and close the parentheses. And then I'm going to turn off the graph for the exponential. So this is my log graph now. I'm going to find the domain first. I'm going to turn off the y-axis because we're only looking at x values. So what do you think my domain is? So what's my lowest x value? It is 0. So if we keep going down, 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 it doesn't look like our graph will ever cross 0. All right, or it gets really, really close to 0. But it doesn't go anywhere further past that. So my lowest domain, or lowest x value, is 0. What's my highest? Infinity. So my domain's from 0 to infinity. Now my range. All right, so I'm going to turn the x-axis off, but the y-axis on. What do you think my lowest y value is? Negative infinity. It'll keep going down forever. What's the highest? Infinity. It'll keep going up forever. I'll bet slowly, but it'll still keep going up. And since it goes from negative infinity to positive infinity, we can also state that it's all real numbers. What do you notice about that domain and range? They swapped. They're opposites of each other. So like I said, because they're inverses, literally everything is opposite of each other. Their x's and y's, their domains and their ranges are exact opposites. Now, let me ask you guys this. If the exponential graph has a horizontal asymptote at y equals 0, the log graph has an asymptote too. But what type of asymptote do you think it will be? It's a vertical asymptote. Where do you think it's going to be at? X equals 0. So logarithms typically have vertical asymptotes or lines that they never cross. So, which is why our domain gets affected with logarithms. So this invisible line right here is our vertical asymptote for the logarithm, and it's at x equals 0. Which again, that's the complete opposite of the horizontal asymptote, which is at y, because they switched the x's and the y's. All right, so that's how exponentials and logarithms connect. They are literally opposites of each other in every sense of the word. If they are true inverses of each other, their domains and ranges will be flipped. Their x's and y's will be flipped. Their asymptotes, type, and the line where it's at will be flipped. All right. So if you know one, it's really easy to figure out the other. Any questions on that? All right, let's look at example 2. So we're going to use our calculator and we're going to figure out what y equals log base 10 of x is and what the domain and range of the graph is. Now, I'm not really going to sketch it. We'll just do it in Desmos. Now, let me ask you guys this. If it's log base 10, that's a review from yesterday, what's another name for log base 10? The common log. So if you ever have log base 10, you can also rewrite this as y equals just plain old log of x. This is called the common log. And that's a review from yesterday. So if you ever see log base 10, you can use the common log. So if I'm looking at my calculator, I'm going to delete these two. I'm just going to type in y equals, go to my functions. And since we have log base 10, I'm just going to hit the common log key, put in x, and there we go. Now, let me ask you guys this. So if we did a quick sketch of this graph, and it's not going to be exact, but if we did a quick sketch of this graph, it'll look something like this. And it's not perfect, but it'll look something like that. So that's just a quick sketch of the graph, just showing its general shape. Guys, heads up, please. All right. Now let's figure out the domain and range. So domain first, I'm only looking at the x-axis. What do you think my lowest x value will be? 0. What do you think my highest will be? Infinity. So this will go from 0 to infinity. What about the range? So if I take the x, give the y, what's my lowest y value? Negative infinity. What's my highest? Right. So we go from negative. Sorry, my watch wants to talk to me today. So we go from negative infinity to positive infinity. So let me ask you this. What type of asymptote do I have for this graph, and where is it? So did the asymptote affect the x values or the y values? It's affected the x values. So what type do you think we're going to have? A vertical, and it's going to be where? X equals 0. So we have a vertical asymptote right here at x equals 0. And again, the way you figure out whether it's vertical or horizontal, vertical affects the x values, horizontal affects the y values. All right. So if the y values are being affected or the range, it's a horizontal. If the x values are being affected or the domain, it's vertical. So I have a vertical asymptote at x equals 0 or just the y-axis. Any questions on that one? All right. Now, I want you to take a look at this graph and tell me which of these functions do you think it fits? And here's a way you can check. My suggestion to you is look at where the vertical asymptote is now, because it is a logarithmic graph. Look at and think about when we did function transformations. Look at the shifts. All right. So take a minute, see what you think. Now, also pay attention to the bases. Yes. Mm-hmm. Any guesses? Jasmine. Say it again. If I had to narrow it down, I would say it's either 4 or 3 based off of their transformations alone. So, the reason it's not 1 and 2 is first off, typically the vertical asymptote for the parent function is the y-axis. All right. It also typically has an x-intercept. Just disconnected. Give me a second. It's been doing this all day. It makes me so mad. So, it also typically has an x-intercept at 1, 0. Now, the vertical asymptote is now here. And it's pretty obvious because it doesn't look like the graph crosses it, which is at x equals -3. That means the graph had to shift to the left 3, which if you remember your transformations, left 3, you write it as something inside the brackets, x, and then you use a +3. All right, so it has to be one of these two. Then, if we look at where the y-intercept is now, it only shifted 2 over, which means that it's probably a different point. So if we actually shift from the x-intercept 3 over, 1, 2, 3, it should have landed about here. But then it's 1 down from it. So that's where we get the -1, because that's the vertical shift. Now, here's how you test what the base is. All right. We did some evaluating logs yesterday. So my suggestion to you is look at where the current x-intercept is. So right here. What's the x-intercept right there? It's at -1. So x is equal to -1. Plug that in for both the x's and see if you get 0. Now you can do this through your calculator. You can do this through Desmos. All right. So if I plug in -1 for both of these x's, -1 plus 3 is 2. 2 raised to the first power is 1. So this all together, if I evaluate it, that means that this should be 1. And again, you can put that in your calculator. And then 1 minus 1 is 0. So, and then this one just won't give it to you. If you put in your calculator, you get some weird number. So your answer is this. You could have also, another strategy you could have used if this was on the EOC, you could have put all 4 of these answer choices into Desmos and start seeing if points started lining up. All right. See if it had that vertical asymptote at x equals 3. See if it had that y-intercept at -1, 0. See if some of the other happy points lined up. That's another method you could use. Because remember, all the tests in this class are calculator active, as well as the EOC. Desmos is your friend here. I just wanted to see if you could do it without looking at it. I mean, it's okay if you couldn't. Desmos is your friend. But essentially, that's what it is. Any questions on that? So again, if you see a graph if you see something like this on the test, put it in Desmos. So I would happily put these in Desmos and match. That's what I would do if I were you. All right. But there is a way that we can figure out the domain or the horizontal asymptote of any logarithmic function. Can anyone guess what that is? So for example, if we look up here, our vertical asymptote was at x equals -3. Now look what the function that gave it to us. Where do you think that x equals -3 comes from? So look at this function here and look at the vertical asymptote. What part of that function do you think could give me the x equals -3? The x plus 3. How do you think I got it? Set it to 0. So the way you find where it is not positive or negative, so the way for finding a non-positive number or it's 0, that's not possible, so the asymptote, also gives you the domain of logarithmic functions. And the way you find that, so to find the domain dash vertical asymptote of a log, set whatever's in those parentheses of that log equal to 0 and solve for x. So for this one right here, what would I set equal to 0 to figure out the domain? 3x minus 4. So I'd do 3x minus 4 equal to 0, and then just solve for x. So you would add 4 to both sides. 3x is equal to 4, divide by 3. X is equal to 4/3. So this is actually the line for the vertical asymptote. So this is where my vertical asymptote is. Because that's going to be the line that's not going to cross. That's going to be our lowest x value. So if I were to write the domain, where would it be? What would have to be my lowest x value for a domain with this graph without even looking at the graph? It can't cross the vertical asymptote, right? So that means the lowest x has to be 4/3. And the highest, if it goes on forever, will just be infinity. So that's a way that you can figure out the domain when it's really not that obvious. Just set whatever's in the parentheses equal to 0 and solve for x. That tells you where the vertical asymptote is. All right. So I don't really care about exercise 5. All right. So now we're going to kind of sum up what we just talked about in that journal entry. So take out that first journal entry that I gave you, the one that looks like this foldable. So we did the exponential side, but we didn't do the logarithmic side. So it should be in your journal. I think it's the very first foldable that I gave you for that for Unit 2. You should have had the exponential side already filled out because we did that in class together, but now we're going to do the logarithmic side. All right. So with logarithmic functions, first off, unlike exponential, it doesn't really have an increase or decrease. I mean, it kind of does, but for this class, we're strictly looking at the increasing versions of logarithmic functions. So this graph right here is kind of the typical graph that you'll see in this class when it comes to logarithmic functions. All right. Now, A logarithmic function always has a what type of asymptote? Vertical. So it's the opposite of exponential. So you can make a note that a logarithmic function is an inverse of an exponential, or it's the opposite. So in other words, inverse means opposite. The vertical asymptote is typically along the y-axis, so at x equals 0. That's how we write your vertical asymptotes. You always say x equals. So horizontal is y equals, vertical is x equals. That's why you have to be specific when you do vertical and horizontal asymptotes and not just tell me a number. Because I'm like, okay, this number goes where? Does it go with x equals? Does it go with y equals? Because it is a line. You got to be specific in that case. All right. Now, if we're looking at the logarithmic graph, we have log base 2 of x. Now, we're going to figure out, I will say that it is the inverse of one of these two functions here. We're going to figure out which one by just quickly calculating its inverse. So when we're calculating an inverse, what's the only thing we got to do first? Switch the x and y's. So I now have x is equal to log 2 of y. Now, all we got to do to solve for y is do loggy froggy. All right. So what I'm going to do is put the x on the other side so that we don't have to do like a backwards loggy froggy. So I'm going to rewrite this as log base 2 of y is equal to x. Same function, I just switched which sides things were on the equal sign. So, who remembers where I always start with loggy froggy? I always start where? At the base. Where's a base in a logarithmic graph? 2. It's that little number. So remember, we start at 2, then we swing around to the x, that's our first checkpoint. Equal sign, that's the second checkpoint. And the y, that's the third checkpoint. All right. And then if we wrote it in the order of b to the x is equal to y, all right, in this exact order. So 1, 2, 3, 4. Those are our steps. What would be the base of the exponential? 2 raised to the what power is equal to y. Good. So if we wrote it with y on the left side, it would be y equals to the x. So that is the inverse of this. So in other words, we can use this table over here to get the points for the logarithmic graph because we just have to flip the x and y's because they're inverses of each other. So I'm going to take a moment and write those down. So I got 1/8, 1/4, 1/2, 1, 2, 4, 8, and it has an extra one, 16. So this would be -3, -2, -1, 0, 1, 2, 3, and then this one's 4. So all I did, the reason I could do that so fast is because all I did was use this table, the y equals 2x table, and just switch the x and y columns. That's all I had to do. All right, that's why I did it so fast, because there was really no calculating involved, because we pretty much already did the math. All right. Now, if I graph this very quickly, it'll look something like this. So 1/8, -3, -2, 1/4, -1, 1/2, 1, 0, 2, 1, 4, 2, 8, 3, and then 16 will be off the graph, so we're just not going to graph it. So it would look something like this. So my blue is my log graph. All right. Now, your vertical asymptote is where for this graph? Where does it look like it'll never cross? Not y equals 0. X equals 0. So even though it's the y-axis, this straight line is technically when x is equal to 0 because it crosses through the x-axis. That's another way you can tell, like, how you know if it's an x equals or y equals. If that line passes through the x-axis as you're going up and down, it's x equals. If it's going through the y-axis as you're going left to right, it's y equals. So this would be at x equals 0. So what would my domain be? So what do you think? So your x values, lowest to highest x values, what do you think? Right. Your domain would go from 0 to infinity. Your lowest x value is 0. Your highest is infinity. What will be my range? Negative infinity to positive infinity, or all real numbers. So essentially, it's the switch of y equals 2x. And that's pretty much it. Any questions on the lesson today? Not too bad, right? All right. So for the rest of class, there is a new delta math. It's the 2.1, 2.3 delta math. So it covers what we learned yesterday as well as today. So take some time, work on that. You can also work on the quizzes from yesterday if you didn't get to that, because we did kind of in class short yesterday. So there is a 2.3 quizzes. You can work on that. You can work on the delta math. Packet work for this one will be page 21, I believe. That's where we'll start. So yeah, kind of pick your poison and get to work. Can you go over test correction? Yes. Okay, so the way test corrections are going to work, and I should have the testing box ready by tomorrow, but in Canvas, so if you're looking in my Canvas page, and I closed it, lovely. So in my Canvas page, I have a module that's solely given to test corrections, and the instructions are posted in Canvas. So, thing about test corrections is your test cannot leave this classroom. So you either have to do them in class, or you have to come after school, or come during your lunchtime to do them. All right, I will not take class time to do test corrections. You have to do them on your own. But they cannot leave classroom. So you can do them like during classwork time. You can come after school if you like. You can come during lunch. I don't really care. All right. Now, basically how it's going to work is with test corrections. I'm almost done kind of cleaning out the box from last semester. So let's not start test corrections until tomorrow. But with test corrections, I have this box right here. It will have all my classes tests in it. It'll be by number. So the tabs on these folders, first off, it's first, second, third period. Yours will be right here, back here, behind the green. I will have the tabs labeled as your student's number for this classroom. So it'll be from 1 to 14. So if you don't know it, you need to see me. All right. Inside the hanging folder is a vanilla folder. That's where I'll put your tests in after you finish them. All right. You would take this out of the hanging folder and pull the test that you want, and you would start the corrections on it. So typically how I do corrections is separate sheet of paper, you need to label unit whatever test corrections, so like unit 1 test corrections. Then you must include, for test corrections to get full credit on them, you must include the number of each question you got wrong. So like if you got number 1 wrong, write number 1, and then you will give me the answer you originally gave. So I don't need you to rewrite the question, I just need what answer you originally gave. I want the correct answer, so what you corrected it to. And then the most important thing, which is highlighted in green on those directions, I either want the work for the correct answer or a quick statement stating why you got the answer wrong initially and why your new answer is correct. So in other words, like, some of the multiple choice questions weren't necessarily something you had to work out. All right, it may have just been a vocabulary thing. I just want to know what your mistake was, So like, for example, like say you work something out the first time, and when you read it, you realize, crap, I wrote down the wrong sign, and that's why you got it wrong. That's what you would say, I wrote down the wrong sign, or sign error, or something like that. I'm basically having you analyze your own work, all right? Now, when you finish with test corrections, you will hand your test corrections to me, all right? Don't put them in the box, don't put them in your folder, put them in my hand. Otherwise, I will not grade them, because I'm not gonna go through this. All right. So if you want test corrections and you want that grade, give them to me. Because I know myself, I will forget they exist here. So put them in my hand. Like physically say, Ms. Murphy, here's my test corrections. All right, cool. I'll put that grade in. So make sure that your tests always go back in the folder and back in the proper spot of the hanging folder. All right. Again, tests cannot leave this room. The reason because we reuse tests a lot. So it's more of a security thing. All right? So you cannot take it home to do. You have to do it in school. All right? Any questions on that? So I'll let you guys start doing test corrections hopefully tomorrow, but I think they just called school. So let me check my email. I saw that during while I was teaching. All right, so you should be either working on your Delta math, your quizzes from yesterday, or something else for this class. Yeah.